Hi, all. Welcome to Theoretically Podcasting. This is Vasu Sham, and I am honored to be joined by Julian Barbour. How are you doing, Julian?
I'm doing very well, thank you. Except I haven't got proper internet connections. I've had to move to my daughter's house, which is where everything has been tied in since they came back from Africa and hasn't yet been found a final resting place, as you can see behind my left shoulder.
Well, I mean, thanks to her for hosting you then, because I'm very excited for our discussion today. So, Julian has been a mentor of mine since the beginning of my scientific career, almost exactly. And he is the progenitor of a theory known as shape dynamics and has made many contributions to foundational questions in gravitational physics, despite not having a conventional academic position. So let me pull up this slide that describes where he's based. So yeah, Julian, tell us a little bit about how it came to be that you're doing what you're doing from where you're doing it.
Yeah, well, quite by chance, back in October 1963, I started asking myself, what is time? And
Hmm.
I have to say, I got completely hooked by that question. And you will appreciate that somebody who wants to think about time is not all that likely to get a position in academia. And by great good fortune, not really for myself, but initially for my brother, who was trying to get into farming. Both of us had a bit of money from my father, not a huge amount. It wasn't enough for my brother to get both land and a house and farm buildings. So I said, well, I'll bid for it at an auction sale and you can live in it for a few years and then we'll sort things out afterwards. So that's how I came to acquire New College, Oxford, New College, sorry, College Farm from New College, Oxford, the day before President Kennedy was assassinated, of all things. It was an eventful time. And
Interesting.
eventually in 1969, I moved in there with my wife. And in this slide, you see me standing at the back door of the house. It's a very beautiful 17th century farmhouse built in 1659. It's got a date stone. And those marvelous birds, swifts, nest under its tiles. And you'll see there's a Latin tag under the words College Farm, Forma Formosa, which you may be able to translate. It means beautiful shape. Uh, Taiwan used to be called Formosa when I was a boy because it was the beautiful island. And
Aha.
as shape dynamics is my baby, I like to think of shapes as being potentially very beautiful.
Right, right. Well, yes, I can attest to the beauty of College Farm, having been there a couple of times myself. And well, let's dive into the shapes then, the beautiful shapes. So, uh, tell us briefly. So I should say that on this podcast we've had on Dave Sloan, and we briefly touched upon the ideas behind shape dynamics, but not in any depth. So it would be great to get your elevator pitch, as it were, for shape dynamics.
Yeah. Well, this again goes back to 1963 because at the same time as I got interested in what is time,
Hmm.
I started reading Ernst Mach's book on the history of mechanics. And
Hmm.
in it, he advocates very strongly that uh, dynamics really should be rewritten in terms of the separations between all the bodies in the universe. And before that, Leibniz had argued along exactly the same lines, I mean, 150 years earlier. Um, and so that Mach's arguments were so powerful that they definitely stimulated Einstein to the creation of general relativity, an absolute miracle. But Einstein set about it in a very indirect way. And I could, because I was in Germany at the time, I could read Einstein's papers. And after a bit, I said to myself, he's setting about implementing Mach's ideas in the wrong way. That's not the right way to do it. So I then got very interested in the question of the relativity of motion. And the first idea I came to was what I called the relative configuration space, which is more or less exactly what Leibniz and Mach had advocated. So the fundamental concept in Newtonian dynamics is the configuration space. That's the position. So if you have n particles, you have 3n coordinates, lots of threes, triplets of three, in which specify the position of each particle. So with n particles, that adds up to three in three-dimensional space. That adds up to 3n coordinates. Now,
Yes.
that includes, though, overall position of the center of mass and a rotational degree of freedom, how the whole system is oriented. So in a way, if you take Mach seriously, you should take that out. And that leaves you with 3n minus 6 degrees of freedom. And that's what I called the relative configuration space. So then I said, and this was in my first paper, which did actually get published in Nature in 1974, a few weeks before the famous paper by Stephen Hawking, in which he had his paper on the evaporation of black holes,
Oh, wow. Okay.
black hole radiation. So in that paper, I said that the history of the universe is a continuous curve in its relative configuration space. And I likened, to get rid of any notion of time, I likened each point in the configuration space, that's each possible configuration of the particles, to a point in a landscape, and sought a geodesic principle which would connect 2 points between different configurations. And that leads to a well-defined theory. Little did I know at that time, and it only transpired another 6 or 7 years later, that without knowing it, I'd recreated what's called Jacobi's principle in dynamics. Jacobi's principle says that if the system has one fixed value of the energy, you can then find the orbit in configuration space as a geodesic principle for one fixed value of the energy. That's Jacobi's principle. Now, Jacobi hadn't arrived at that principle, which he did in 1837. He hadn't arrived at that to get rid of time, which was my ambition. His was more modest, which was just to, yes, there it is. Equation 10. That's very clever of you, Vasudev, to show it up there. So it has a very typical characteristic square root sign, E minus V, times something which looks like the kinetic energy, except that the lambda is an arbitrary monotonically increasing parameter. And so Jacobi had introduced that principle just to tidy up the mathematics of the principle of least action, which had been developed by Euler and Lagrange. If I may say so, my ambition was greater than Jacobi's. I wanted to get rid of time altogether, not to put it on an appropriate thing. And just as a matter of interest, when I did check out, it's an interesting story. I went to the library in Oxford to check out Jacobi's great book, the Lectures on Mechanics, Vorlesungen über Dynamik. Well, the first thing that was found, it's one of the most famous books in dynamics. And I had to ask the librarian for a paper knife to cut the sheets, because I was the first person in 140 years to want to look at the book. But then I found that the form that actually Jacobi had used didn't have the lambda in at all. It just had. So if you take away the d lambdas, that's the
Yes.
form that you find that Jacobi used. You just have the increments of the change in the positions, the drs, the change in the positions of the thing. So normally what one uses Jacobi's principle. In fact, every student who's solved the Kepler problem will have used Jacobi's principle, because they will have first of all used polar coordinates with an angle and a distance to the particle, and they will have found the orbit of the particle, a timeless orbit. They will have found the elliptical orbit, and then they will have used the energy theorem, conservation of energy, to find the speed in orbit. But if you're talking about the whole universe, so in Jacobi's case, that presupposes that there's a clock outside the system which is telling you the time. So in the case of the solar system, it might be the rotation angle of the Earth, but that's not that's something quite distinct, effectively, from the orbit, say, of Mars, which you might be wanting to determine. So if you're talking about the whole universe, there is no clock outside it. So therefore, you get an equation. I don't know whether I show it in there. If you can go on to the next page. Yes, I do. You see there the equation 12. That's what the equation of motion looks like. And you get this curious factor on the left, E minus V over T, and then its inverse on the other side. And that's a very strange looking equation. And I said to myself, well, that needs to be simplified. And you can, because the T, which looks like a kinetic energy, but it's not, because it depends upon this arbitrary parameter lambda. So you can give it any value you like. So you can give it a value, you choose it so that T has the value E minus V, and then that makes that awkward factor unity, and it just disappears from the equation of motion. And then suddenly you find you've got Newton's second law of motion, and your special choice of lambda looks like time. But that means what you've done is you found an emergent time. You found a way of defining time for the whole universe. So there isn't a pre-existing time. It just emerges out of the geodesic law that you formulated for the universe.
Right.
And then, in addition, in the standard treatment of Jacobi's principle, that E has can have different values, because it really corresponds for given displacements. If you go back to the previous page, for given displacements dr if it's dr by dt, for given displacements, different amounts of time can pass. And that means that you're giving initial conditions with different velocities and different total energies. But that's only possible because you've assumed an external time, and that's what makes it possible to put that E there. And in fact, when I came up with my proposal, I didn't have an E at all. I just had something like square root of V times T, because it hadn't. I wasn't interested in recovering time at all. So basically, you would just say, if you're doing this purely relationally, as both Leibniz and Mach would require, and that's what I did, you would just write down, you would just have V multiplying T, and if V is negative, as it is for the Newton gravitational potential, then minus V will be positive, and everything will be hunky-dory.
Right. So this was your path to the relative configuration space.
That was my path to the relative, and it was also the path to a wonderful collaboration, because about a year, after that paper had appeared in Nature, I got a letter from Italy, from Pavia, one Bruno Bertotti, who was a very well-respected theoretician, both a theoretician, but he's also very interested in experimental gravity. There were just two figures in the world who really got experimental gravity going. The first was Bob Dicke in the United States. And the person who most closely worked in the field was Bertotti. And in fact, yes, so Dicke organized the first international conference on experimental gravity, and Bertotti the second. And I attended it in Pavia about a year, no, only 6 months after, I think it was 1976, or might even have been as early as 1975. Just very soon after I'd started interacting with Bertotti, and I met some very, very interesting people. Now his name will escape me. I'm getting terrible at remembering names, but one of the persons was working closely with Dicke and was supervising one of these landers on Mars, which was checking general relativity to a high accuracy and things like that. So that was and ever since then, I've had that feeling which I really imbibed from Bertotti of, trying to touch nature ever so delicately to, get its secrets by these wonderfully precise measurements that can now be made. So that then led to very successful about 6 years working with Bertotti. And what was really important was the way I'd chosen to implement Mach's principle was, I wasn't the first to do it. In fact, over the course of the 20th century, about 10 or perhaps more people quite independently rediscovered exactly the same way. The first person who'd proposed it was back in 1904, a Viennese engineer who actually got to talk to Einstein, which was how that became known. But then Reissner of the Nordstrom-Reissner solution, he had found it, and sort of slightly aware of Reissner's work, but effectively independently, Schrödinger had rediscovered it in 1925, and it's pretty well, I think, his last paper before he created wave mechanics, and then a whole lot more, and I was one of them. Now, Bertotti, being so sensitive to experimental tests of gravity, immediately saw that although the theory was very attractive from a Machian Leibnizian point of view, it had a fatal experimental flaw, which was that it would predict effective anisotropic inertial mass, and the galaxy would perturb the motions of the planets in the solar system in a way that would be quite ruled out now. In fact, Schrödinger was well aware that his theory was already at the limits of what might be ruled out by experiment. And in fact, actually, there's a nice paper by, now I remember the name of the person, no, one of the people, sorry, it's Ken Nordtvedt, who has the Nordtvedt effect. He was the person who was an undergraduate, I think he was, had that idea, that brilliant idea of putting reflecting mirrors on the moon so that they could send laser signals to the moon, and that over time the accuracy would increase. So now I think they measured the accuracy of the distance to the moon to about 1 centimeter, if not even better. And it's an incredibly sensitive test of of gravity. But there's also a brief short paper with Nordtvedt from, I don't know, about 1973 perhaps, where he just very simply shows that the galaxy will perturb the solar system in a way, the planets in a way that's completely ruled out. So then the question was, how do we get around that? And then interestingly, I'd already, before I even met Bertotti, I'd been thinking of a way to apply Machian ideas to field theory. And that wasn't possible in the same way that I'd done with particles. So I'd come up with the idea of best matching, which was
Hmm.
somehow to imagine that you had two field configurations which were almost the same, but not identical, and then try to move one relative to the other, like I'm moving my hands relative to the other, until they get as close to overlap as they possibly could. And I now call that procedure best matching.
Hmm.
And interestingly, I did discuss it with, in 1973, this was 2 years before 2 or 3 years at least before I met Bertotti. I discussed that with Charlie Misner, who was on sabbatical in Oxford, and I had an introduction to him, and I described that method to him, and he said he thought it was really quite interesting. What neither of us realized at the time is that it's the origin of the linear constraints in the ADM formalism in the theory of gravity. It's one of the most important facts about general relativity. But what that does is minimize the, so to speak, the incongruence between the two. And you can do it
Right.
just as well with particles as with that. And that actually has the great virtue of eliminating yes, there you've got the equations there. I don't know whether we need to go into it in great detail, but the key thing is you start with the Newton kinetic metric, which is
Hmm.
in equation 16, isn't it? I think yes, and
Yes.
then you use the generators of the Euclidean group, translations and rotations, to bring it to a minimum. Um,
Right.
and that the key thing about that is it reduces it means that your initial condition is of angular, it gives you exactly vanishing angular momentum, which is a very
Hmm.
marked requirement. And then because the Newton gravitational potential is invariant under the Euclidean group, that condition is propagated by the equations of motion. So you've got a perfect theory. It's a Machian theory. You can say also that the energy must be zero because there isn't any absolute time. So then there is this work singles out a subset of Newtonian solutions, a very small one,
Hmm.
for which the energy and the angular momentum are exactly zero. And that's
Right.
very satisfactory. And Bertotti and I published that in a paper in 1982. It was whatever is the expression, I can't remember. Roger Penrose very kindly communicated it, that's the word I think, to the Proceedings of the Royal Society, where it was published in
I
19.
see.
Um, and in fact, it was only 2 years before that, when I visited Karl Kuchasz in Salt Lake City, that we finally realized that it was Jacobi's principle and not Gauss's principle of least constraint that he had originally thought it was. So all of that was very nice. And that paper, I think it's fair to say that paper of Bertotti and myself is now regarded more or less as the way to implement Mach's principle. And as we were discussing when you visited me a few months ago in South Newington, that idea of best matching really underlies a whole lot of things that are going on in artificial intelligence, recognizing shapes and things like that. So yeah, I think it's, after all, congruence, establishing congruence is the most fundamental tool in proving results in geometry.
Yes.
So I think we're on the right track with this idea.
Yes. So
Yeah.
so we've so far talked a lot about the sort of Newtonian n-body problem type situations, basically particle models. But it's worth sort of mentioning that there is a parallel of this formalism in the like the fully sort of field theoretic gravitational case. So basically, you have like you had a Jacobi-like principle, action principle for the metric, as in you had an equivalent description of general relativity in terms of this, and you were also able to include matter fields and so forth. So Tell us about how that work came about. So when did you?
Well, well, this is all to do with the really fundamental importance of group theory. I mean,
Mhm.
the Euclidean group, which is so important for so many things before you get to all the wonders of general relativity.
Uh-huh.
It's a group which depends upon a finite number of parameters. There are 3 for the translations and 3 for the rotations. Now, when you come to general relativity, you have groups that depend on arbitrary functions. You have the
Yes.
3-dimensional diffeomorphism group, which is what leads to the linear constraints in the ADM formalism in general relativity of Arnovitz
Yes.
and Misner. And you also have the 3-dimensional conformal group, which we may come on to in a bit. And you're actually using the groups in exactly the same way. You're using them to best match. The only difference is now the groups do not depend on a finite number of parameters, but on a finite number of arbitrary functions, of functions that are in principle arbitrary. But
Right.
otherwise, the conceptual framework is identical, as in fact I was already exploiting when I talked to Charlie Misner back in 1973 in his office in Oxford.
Right. 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 So indeed, let's jump into the conformal part of the story, and we have finally reached the shapes of shape dynamics.
Well, I would say yes. Let's not go. There's this nice expression, whole hog, the whole way.
Okay. Okay.
Uh, but first of all, stick with the particles
Sure.
because
Sure. So yeah,
yeah.
let's yeah.
So they're the conformal ones are just they're just reduced to changing the scale.
Yes.
So you have an overall change in scale. So if you have a triangle, if you have an equilateral triangle, you just imagine it either smaller or greater. Um, and at the end of the time I was working with Bertotti, we certainly every now and then said, well, really, we should extend our ideas to include dilatations, which would mean
Hmm.
we would go from the Euclidean group to the similarity group, which is the fundamental group of Euclidean geometry. And we thought, well, we didn't think it would lead to much of great interest. That was the
Okay.
biggest mistake we made. So we never got round to doing it. And then in 1993, I was the joint organizer of a wonderful conference in Tübingen on Mach's principle. I was the joint organizer with Herbert Pfister. And the great English astrophysicist Donald Lyndon Bell, who was very interested in Mach's principle, was there. And in one of the discussion sessions at the end of my talk, he asked if it could be extended to include scaling. And I
Hmm.
said, yes, I was pretty sure it would, but I didn't go any further than that. Anyway, Donald, who sadly died about 18 months ago, didn't leave it at that. And he had actually been, and he had identified himself as the referee of our 1982 paper to
The
the
Royal
Royal
Society.
Society proceedings. He invited me over to Cambridge to have lunch at his beautiful college, Clare College, which is the one that stands next to King's College with its magnificent chapel. And
Hmm.
there again, he pressed me to make it scale invariant. So then I thought, well, I better get down to this. Uh, and bit by bit I did. And in fact, it happened. So I felt I need to get help from people who work on the n-body problem, the problem of
Hmm.
n point particles interacting in Euclidean space gravitationally. And by then I knew that a very well-regarded specialist was somebody called Christian Marchal in Paris,
Hmm.
who had written a book on the three-body problem, which I'd bought. at great expense, I may say.
I see.
So I got in touch with him and asked him if I could come and see him, and I did, and that was helpful. And it was while I was in Paris, where my son had moved by that stage, and I was lying in bed, and suddenly the way to think about making our idea scale invariant came to me, and it was on my birthday, very appropriately. Things always seem to happen on my birthday in Paris. It's wonderful. It's at least 3 or 4 important events have happened there. And so then immediately from there, I went to Dublin because I'd been invited by the Students' Philosophical Society at Trinity College Dublin to give a talk on my ideas that time didn't exist, because by then my popular science book, The End of Time, had been published, and well, it was about to be published.
I see.
And they'd got wind of that. And then I thought, well, I'll take advantage of a tip that had been given me by Jimmy York. So we'll come to Jimmy York in a while. Because he'd done very important work on the initial value problem in general relativity, and I'd had the luck to interact with him and visit him for 6 weeks in North Carolina. And he'd given me a wonderful tip. He said, I'll tell you the person who will really help your ideas. That's my first doctoral student, Neil O'Murrochu at the University of Cork. So I sent email to Neil and said, Neil, I'm going to be in Dublin giving a talk on such and such a date. Can I come over and visit you in Cork and talk about some ideas? And he said, do come. So after the talk in Dublin, I went to Cork. We got on very well, and Neil said, oh yes, we can extend your idea to look at general relativity and have a new theory. The aim was to have a theory which wasn't general relativity, but was scale invariant in a way that general relativity wasn't. And then after about 2 days with Neil in Cork, I then flew to the United States. And on the flight, I did my one and only mathematical calculation, which in some senses was a new result. Little did I know it had been done in 1771 by Lagrange in a famous paper. But what it showed was that the idea that I had worked, but was problematic. It showed that if you make Newtonian theory invariant, not only with respect to the Euclidean group, but also with respect to the similarity group, the dilatations, and do it by best matching, then you finish up with a result which says that the size of the universe can't change. It remains constant. It just, it stays constant, and all that happens is some of the particles move a bit closer to each other, and then they move further back. You can reproduce Newtonian gravity locally very exactly, but you get additional forces, which are the ones that make sure that the size of the universe can't change. So for a long time, that was where the situation stayed. But before that, still wanting to talk to n-body specialists, Bertotti had spotted a paper by 2 people, Littlejohn and Reinsch, published in Reviews of Modern Physics in 1996. And he gave it to me when I visited him in 1997, the spring of 1997, and said he'd realized that there was very interesting mathematics there to do with non-integrable connections, which we hadn't realized. And he said he was going to work on it. Then a couple of weeks later, he said, it's too late. Look at this paper by Littlejohn and Reinsch. And this was very interesting. And that I could see that these guys knew something. So I sent an email to Littlejohn and said, I'm going to be in the United States at the middle of March 1999. is there any chance I could talk to him about making the Newtonian n-body problem scale invariance? And he wrote back and he said, I can't tell you anything, I'm afraid. You're very welcome to come and see me if you're coming to California in Berkeley. But the only person I can think of who might be able to help you is Richard Montgomery in Santa Cruz, which is not far away.
Uh-huh.
This set up my visit there, and it was wonderful because I did see Little John. I talked to him. I went on from there to Santa Cruz with my wife, and I had a very intense 3 hours discussion with Richard Montgomery when he really introduced me to some of the really key and exciting concepts in the Newtonian n-body problem, which is a lot more interesting than anybody except n-body specialists realize. It's all to do with the conditions under which all the particles can collide together at a given instant at their common center of mass, or they can all escape to infinity, just escape to infinity in a solution which is called parabolic escape. Anyway, so I had a very intense 3-hour discussion with Richard, and he introduced me to the key concept, the shape potential, a wonderful way of representing shapes of triangles for the three-body problem with what's called the shape sphere. And then in addition, he said, and I'll tell you what, there's 2 mathematicians at the observatory in Paris. I'll introduce you to them, and they'll be the people to really help you. And I've been interacting with those 2, Alain Chancinet and Alain Albouy, now for close on 24 years. I think it'll be 24 years in a couple of months. And a great deal of what has come out recently has come from that wonderful interaction. And then what is a very nice touch, so Richard escorted me from his home down to downtown Santa Cruz, where my wife was waiting for me in the recreational vehicle we'd hired. Then he got on his bicycle and cycled back home. And on the way home, the last piece in the jigsaw puzzle of a solution to the n-body problem on which he had been working with Alain Chancinet, the older of the 2 n-body specialists in Paris, fell into place. And I think it is the first non-trivial and really interesting solution of the n-body problem found since Lagrange worked in 1771.
Okay.
And it's called a figure of 8 solution. It's got negative energy, and 3 particles follow each other around in a figure of 8. And it's stable against small perturbations, which is a great discovery. And if you read the paper by Richard and Alain Chancinet, at the end of it, you'll find that Richard thanks Julian Barbour for an inspirational discussion. Yes, there you are. Goodness me, very good of you to pick that up. There you go. This is what's called a choreography.
Right. The remarkable thing is that this is a valid solution to the 3-body problem.
That's right. Yes, and then it stimulated ones where there are more particles doing what are called choreographies.
Oh, wow.
So I asked Richard, what did I help? He said he couldn't pin it down, but he said it was just that intense discussion that had clearly sort of got his brain cells working in a second. This is very beautiful.
Wonderful.
How clever to get that like
Google helps, yeah.
Yeah.
Well, so that's great. So you, in passing, you've mentioned the shape potential and all that has come of it, the insights that have come of it. So let's go there. So what is the shape potential and why is it so important?
Well, the shape potential is very important because it's scale invariant. So the Newton potential has 2 wonderful, very virtuous properties. It's unchanged if you move the whole system through space, translate, or rotate. And that's why angular momentum and momentum are conserved.
Right.
Uh, but it's not invariant under dilatations. The value, obviously, the value changes because it's the gravitational potential is a 1/r function,
Yes.
and if you increase r, it just goes down. So the shape potential. So there's really just two quantities which are determine the n-body problem of a finite number of gravitationally interacting particles. There's just two quantities which are really important. One is obviously the Newton potential, and the other is the root mean square length. You take all the separations between the particles, add them up, weight them by the masses. Yes, here we.
This is the let's go to here it is.
No, here it is. Yes, in equation 11 on the left, there's the expression for the root mean square length. You divide by the total mass so that you get something which it doesn't depend on the mass scale. You take the product of you take each pair of masses and take it multiply them together, and then multiply it by the square of the separations. You add up all those things and take the square root, and that's the root mean square length. And that, along with the Newton potential, those are just the two quantities. The n-body problem is all about those two quantities. And so the shape potential is, in fact, what you get if you multiply the Newton potential by the square root by the root mean square length. So that's in equation 5 there. You see it there. You have to divide by m squared to take the mass factor out of the Newton potential. So there in equation 5, there's there. Now, if you look at equation 4, we call my collaborators and I, that's Tim Kozlowski, Flavio Mercati, and myself, we call it the complexity. And we did in our paper that appeared in Physical Review Letters in 2014, we call it the complexity because it's a remarkably interesting quantity. So it's a ratio of two lengths. That's what makes it scale invariant. Now, the denominator in that expression is the mean harmonic length. Now, the mean harmonic length is actually the inverse of the Newton potential.
Right.
And so the root mean square length is really the average of the long separations between the particles, and the mean harmonic length is the average of the short ones. So its ratio, which is what we call the shape complexity, or it is the shape potential, up to a sign, they're exactly the same thing. You can call it the diameter of a shape, because how do you measure something? How do you measure a long distance? Well, you take a short ruler and you see how many times it fits along it. So in a way, if you want to say how big is a shape without assuming that ridiculously assuming you've got a ruler outside the universe to measure it, the only way you can do it is by looking at the separations within it. So the thing that you're led to very naturally is this quantity, the shape potential. Now, we call it the shape complexity because if you have a reasonable number of particles, say anything more than 6 or 7, if 2 or 3 of them move closer to each other, the root mean square length changes very little. If you have enough particles, even bringing 2 particles to coincidence will have virtually no effect on the root mean square length, but it'll have a huge impact on the mean harmonic length, which is the inverse of the Newton potential, which will make the mean harmonic length tiny. So the shape complexity, this expression defined in 4, will become huge. So it's a very sensitive measure of clustering, and therefore of structure or shape.
Right. Right.
And I think this is interesting because for me, it's a fascinating experience for me. Back in 1977, something prompted me to read about Leibniz's philosophy.
Mm-hmm.
And Leibniz, whom I may say is, regarded as one of the really greatest philosophers. I mean, Gödel apparently said, he was the one logician he really respected. Leibniz says, I mean, if you read his philosophical papers, a thing that's really running behind it all the time is that if there were no variety in the world, there would be nothing. You couldn't, there would be nothing to say. I mean, literally, there is nothing. Without variety, there's nothing. And therefore, Leibniz was believed in perfection. And therefore, he said, really, in his monadology, he says that we live in the world which is more varied than any other possible world, but subject to the simplest possible rules. Now, that's not quite an accurate statement of his philosophy. If you read all of them, it's much more what he's actually really saying is that because he believes in perfection and the universe should be striving to perfection, complexity or variety should be increasing all the time.
Interesting. Okay.
Yeah. And back in 1990, when was it? 1980, I first met Lee Smolin, and I introduced him to Leibniz and this idea about variety, because that had made a big impression on me. And then Lee came up with a mathematical model for realizing maximum variety in a universe. And we have one solitary joint paper on the subject on maximal variety, which does get actually quite a few citations, amusingly. And we worked on it on and off for a few years. But then I began to feel that although his mathematical model was clearly a consistent one, which relied on views of the universe from different points of view, I came to feel it wasn't really working. So I was always on the lookout for an alternative way of expressing variety. And I remember very clearly about 2011, on one of my visits to Paris, I was talking to Alain Albuy, the younger of the two N-body specialists there, and got talking to him about the shape potential, saying, wouldn't this be a good thing to characterize the variety in the N-body problem? And that stuck in my mind. And then it's too long a story to go into exactly how it happened. That was then what led to the paper in 2014 with the Arrow of Time. So yes. A little bit more background for that is necessary, if you can bear with me.
Sure, of course.
And whoever happens to be watching this can. Now, what had happened in 1771 is Lagrange had found, by very simple calculation, as it turns out, the first qualitative result in dynamics. That is a result which follows directly from the form of the law and must happen in every single solution. And he had shown that root mean square length that we discussed before, he found what the behavior of that is. It has a universal behavior if the energy is either negative, which is what you would want from a Machian Leibnizian point of view, or positive. And if that's the case, then in the infinite Newtonian past, the root mean square length is infinitely great. It steadily decreases with Newtonian time down in virtually all the solutions to a finite value and then increases again to infinity in the infinite future.
Okay.
And that's the first qualitative result in dynamics. I read about it in 1982, and somehow or other it stuck very firmly in my memory. And then in about 2011, 2012, Flavio Mercati, who was working with me then on Machina, we applied unsuccessfully, as it turned out, for a grant from the Templeton Foundation, which was being the applicants were being chosen by the University of Chicago, and I think it was something to do with structure in the universe or something. Anyway, this led me to suggest to Flavio that we put forward some proposal. And it was while writing that proposal that it suddenly occurred to me that that point of minimum size, which I now call the Janus point, is so the minimal size you can't see within the universe. That's measured by some imagined external ruler. Within the universe, there's the plot we got. Within the universe, in the vicinity of the Janus point, the particles have a more uniform distribution than anywhere else. That's the artist's impression of it there. It's like a swarm of bees. The distribution is more uniform than anywhere else in the solution, and the particles are all sort of moving in random directions. It's where the system is closest to thermal equilibrium. And then as you go in both directions away from it, by the way, the complexity graph above it, that's the result of a 1,000-body calculation by Graham. So what's his surname? I'm getting so bad with names. Anyway, he'll forgive me.
Jerome Barkley.
Sorry? Barkley, Jerome Barkley.
Yes.
Yeah, thank you. That he did, it's a 1,000-body simulation of 1,000 particles. And you see the complexity growing wonderfully well. And basically what that means, well, this is only the early stages, but what that means is then that as you get away from the Janus point in both directions, clusters form. In those clusters, you get systems which can be like our solar system or even our galaxy. And particularly interesting, you can get Kepler pairs. That's two particles going around their common center of mass in Keplerian orbits. And the orbital elements get ever more stable as you get further away from the Janus point. And these Kepler pairs, they are actually rods, clocks, and compasses all in one. They're clocks because every time an orbit is completed, that's a tick of the clock. The length of the major axis is your measuring rod, and its direction is your compass direction. And all of these Kepler pairs become increasingly to ever more digits in their decimal expansion of the orbital elements, become ever more perfectly synchronized, and it's fantastic. It is actually the most extraordinary creation of order out of disorder, and it happens in every single solution. Now, this is completely different from the standard story in thermodynamics and the normal explanation of the arrow of time through entropy, in which it is said to be due to increasing disorder, and you can only see it in a collection of solutions, in a Gibbs ensemble of solutions. It's not in every micro solution, where in this case it's in every micro solution. So, so this led to our paper in 2014 in Physical Review Letters, which they obviously thought was quite important because they sent it to no less than 5 referees, of whom of whom 3 were very positive. One said, well, didn't think it was quite enough because we'd only established 1 arrow of time and there was a whole lot more that ought to be explained.
Uh-huh.
The last one said this paper can't be published because it's wrong, but didn't explain why. So we could ignore it. So we
Okay.
modified the
So this is
referee.
the paper.
Yes, we mollified the referee who wanted us to do more and say, well, this is only a first step, but it is actually quite an interesting one. And we conjectured that possibly all arrows of time might be explained eventually. Now, I think the reason why this result took so long to discover, to come to light, it's very interesting. I think it's a combination of conceptual inertia. So let me talk about that first. So
Okay.
thermodynamics was discovered through the study of steam engines. There was a wonderful little booklet published in 1824 by the Frenchman Sadi Carnot, trying to establish when steam engines would work with maximal efficiency. It's a superb job. He didn't quite finish it off, but he got pretty close. And then through the efforts of William Thomson, who later became Lord Kelvin, in 1849, so 25 years later, he published a longish paper in which he introduced for the first time the expression thermodynamic. That paper was read almost immediately by Rudolf Clausius in Germany, who literally within a month or two had got both the first and the second law of thermodynamics. The second law of Carnot was very close to them both, but Carnot still believed that heat was some special fluid. He didn't think it was sort of for the motion of particles. It was called caloric. So Clausius very quickly got both of them and published a paper on it, and independently, though not beating Clausius to the publication, Kelvin, as he wasn't yet, William Thomson, had also arrived at the same thing. So essentially, the first 2 laws of thermodynamics were discovered more or less instantaneously. Now, a key feature of this was that it all came from study of a steam engine. Now, a steam engine stops running if the steam escapes from the cylinder, the steam box. So you have to have a confined system.
Yes.
And this was absolutely critical in Clausius's marvelous definition of entropy, where he imagines a system which is always in thermal equilibrium or just slowly being adjusted from one thermal equilibrium to another by changing the pressure or the heat input and things like that. But it's got to be in a box to control it like that. And also, if you look at the theoretical papers, the first really significant one is also by Clausius in 1857. It has the title on, what is it, on the phenomenon that we call, on the motion that we call heat or something. I can't remember the exact. Yeah. Anyway, Clausius is the first really important one. Maxwell picks it up and publishes a very famous one, which gives the famous Maxwell distribution for thermal equilibrium. Then Boltzmann picks it up, and finally Gibbs is working on it. Now, in all of these things, if you read those papers, you'll just see that they're imagining particles, they can be molecules, which are bumping into each other either elastically or inelastically. And generally, they're bumping off the walls of a box elastically.
Yes.
And that's why the system it can equilibrate and tend to a maximum entropy. So you, for example, you have a box filled with air, and in one corner there's an ice cube. Well, bit by bit, the ice cube will melt. So the ice cube is a lattice structure and very highly ordered. Bit by bit, the ice will melt and become water. Then the water will evaporate, and water molecules will fill the whole box uniformly. and that's maximal entropy. And that's basically what led Clausius in 1865, in the paper in which he coined the expression entropy, to say that the energy of the universe is constant, the entropy of the universe tends to a maximum. But amazing, it is absolutely amazing. You look through all the papers on the arrow of time and thermodynamics, the whole thing, you'll find it damned hard to find anybody who asks, what happens if the box is not there? Quite extraordinary. I sometimes think I was the first person to actually say, what happens? Is the universe in a box, and does that make a difference?
Well, yeah, I would say that in a lot of contemporary theoretical physics, the access to a box is indeed one of the major impediments, or the lack of access, rather, to a box is one of the major impediments to making progress on bringing some of the fancy tools we have to bear on physical questions. So your point is well taken. And yeah, I'm just yeah, I would indeed like to hear where to go when you don't have a box. So
Yeah,
say we
well,
just couldn't.
I mean, the answer is at least go to the Newtonian n-body problem. That is not in a box, because the root mean square length, if the energy, well, the root mean square length in almost all cases can and will become infinite. It will grow to infinite. If the energy is non-negative, it's bound to in both time directions. Even most of the bulk of the negative energy solutions will break up, and the root mean square length will become infinite. I mean, I don't know how many negative energy solutions are now known. That beautiful figure of 8 solution that you so cleverly brought up, you were well prepared, wasn't it? That remains stable forever. But
I see.
But it won't really, if any particle comes close to it and makes a big enough perturbation away from its stability value. So that's an example of a system. And in fact, as I just explained, the behavior is exactly the opposite of what happens in standard statistical mechanics and thermodynamics. You get order created, and mathematically, you have this in dynamics. You have the concept of a shape of a phase space, and the solutions can either explore a phase space which has is compact, or has a finite Liouville measure, or alternatively, it can explore one that has the solutions can explore an infinite volume of phase space, a Liouville volume, and those are two completely different. They're like night and day, and I think this is just the whole business of, if we're on the right track, this is the whole distinction which has been completely missed. If you read Gibbs's book from 1902, 1903, right at the end of his life, where he writes this absolutely classic on statistical mechanics, he develops all his wonderful theory, and then with the Liouville theorem, where the measure of a Gibbs ensemble is conserved, he says that he must make a caveat that his theory will only work provided the system cannot explore an infinite space, or the momentum can get arbitrarily large, because in that case, he hasn't got a proper probability measure. And this has just been missed by the great bulk of the people who write on these things.
But versions of this question do come up. Well, I'm sure that you've heard of the whole debacle of the measure problem as it pertains to early universe cosmology, where basically taking certain inflationary models, or usually inflationary models, and sort of trying to debate how much sense it makes to talk about how probable inflation is, how probable the universe is, and just realizing that having infinite volumes makes it hard to assign probabilities. And
Yes.
our mutual friend Dave Sloan has spent a lot of time trying to bring some of the sort of this shape dynamical wisdom to bear on that problem, which I guess, I mean, that's a separate conversation. But indeed, there's manifestations of this question that have come up, but indeed, it's not been I mean, the at the heart of it, it's always been a question, or it's always seen as a matter of truncating space somehow. Or at least most of what I've seen is like, well, just kind of say there might be a box in one or the other way, and then proceed.
Yeah, well, actually, well, first of all, let me say that Dave Sloan, in a way, was onto something essentially our result before us, but in a way. Now, the really interesting thing about shape dynamics, or shape space, the space of all possible shapes, is that, and we can discuss it for the Newtonian n-body problem. The Newtonian n-body problem has an infinite phase space, because the root mean square length can become infinite. Just the configuration space, the configuration part, is already infinite. But the key thing is, when you quotient by dilatations, you make shape space compact. And that means essentially it has, in fact, actually, it's got a finite volume, which is a pure number. In the three-body problem, it's a shaped sphere, so its size is literally 4 pi. There's no arguing about it, pure number 4 pi. So that, first of all, means that although in the normal representation you've got solutions which explore an infinite phase space, when you take out scale, there's the shape sphere. When you take out scale, you get a compact space with a finite volume, but in it, the dynamics is no longer Hamiltonian. So you don't get it. So, and this was actually the point that Dave Sloan got independently, that you get this, what's exactly the way he puts it, but
the dynamical similarity, you mean?
It's the dynamic. So if you're in dynamical similarity, if the potential is, I don't know that dynamical similarity is absolutely essential, but it's certainly the way Dave Sloan got to it. If the potential is homogeneous of some degree, then you lose 1 degree of freedom, because if you change the scale and change the time, the system runs through the same shapes, but at a different rate. But if you can only see the successive shapes, then that's what it is. Essentially, as Tim Kozlowski says, taking out, doing that dilatation, it's dynamical similarity, it's dynamical similarity decouples the time and distance from the other degrees of freedom, and then therefore you're left with that, they become unobservable, and you're left just with an unparametrized, undirected curve in shape space. And if you go to the next one, we'll see what it looks like. Yeah. So on the left is what we show. So that's the shape sphere. Let me just say a little bit about that. The color coding gives you the complexity for the three-body and this is the equal mass case. The absolute minimum is at the equilateral triangle. Then there are 6 special points on the. So each point corresponds to a triangle shape, and points with the same latitude, the same longitude and opposite latitude are mirror images of each other. And on the collinear triangles, which are still triangles, are on the equator, there are 3 points which are called two-body coincidences, where two particles in the limit get coincident and are therefore much further away, are much closer to each other than the third particle. And that's what makes the complexity in that sort of mauve region go infinitely high. So it goes to a infinitely thin, infinitely high peak at each of those 3 points. And then in between them, there are saddles. You see quite clearly there are saddles of the complexity, and they are so-called Euler configurations. So that's the shape sphere color-coded. And then if you look on the right, you see a solution which is got a Janus point. So if perhaps you can, there should be, yes, just move, you'll see there's a little white cross on the rear there. You've got it. That's the Janus point there. And in the Newtonian representation, that's where the size is minimal. And then the two solutions that go out in opposite directions from the Janus point, one is in yellow and the other is in red. And you see that they climb up the complexity mountains, and they wind ever around. So I would, that paper that I think you're showing now has got the title Gravity's Creative Core. So
it certainly does.
When you
It certainly does. So let's just scroll back up.
I would say when you take away, that's it, thank you. When you take away when you purge Newton's theory of all its absolutes, then you find really what is happening is shapes are changing, and the shapes have a the evolution always has a first of all, you can define geodesics. Those are those scale invariant ones that I talked about earlier. Those are geodesics. On the shape sphere, they're just great circles, and nothing particularly interesting happens. The system is always just going round and round. It's Poincare recurrent. There's no arrow of time. It's Poincare recurrent. But what happens in Newtonian gravity, when you look at it in terms of shapes and forget all about absolute space and time and a ruler, is that curve always, the physical curve, always had a tendency to climb the complexity mountains. And that is it is creating structure. So that is why that's gravity's creative core. And I would say that is the real essence of Newtonian gravity, which I don't think has been properly appreciated before. I mean, it's of course, it's implicit in our paper from 2014, but I came on this because actually the paper is to quite an extent disagreeing with a paper by Carlo Rovelli about entropy and things like that. We don't need to go into that, but anybody who wants to read about it can check out.
Yes.
And see.
On that topic, I was actually curious. So just going through your recent papers, I ran into this paper, which I missed when it first came out. But I found it very illuminating. And I mean, I've already started to recommend it to friends working not just in physics, but also in computer science, machine learning, and so forth. Yes, so
yes, I should say that that's basically the work of the two collaborators, Gabriele and Christina, who's his wife, who are at Ann Arbor. My part in that was, first of all, I invited Gabriele to come and work with me for a week in College Farm, where but I'd met him at a wonderful workshop in the Black Forest a few months before, and we hadn't. Tim Maudlin, the philosopher of science, had given a talk about the different forms of entropy, which had left both of us not totally persuaded that was the right way to think about it.
Yeah.
So I got talking to Gabriele, and I very soon found we were very much on the same wavelength. So he came. And so I would say my contribution to that was, first of all, hospitality in College Farm for a week, and more the initial intuition, which I shared with Gabriele, but the bulk of the work is his. But I think it's very nicely done. Particularly, there's the discussion about the finches in the Galapagos Islands and
Yes.
like that.
Well,
And I think it's very good. I think that use I can't remember whether he or I landed on this word variability. It might be me because I've always been interested in variety, but I don't
right.
take any of the credit from Gabriele and Christina because, as I say, they did the bulk of the work. But I think I'm very happy with that paper, and it is beginning to get cited.
Yes, and so what I was wondering was you made a very compelling case, at least in the Newtonian n-body universe, that the crux of the matter, what's actually happening is that the shape complexity is growing. So how do we square that with what in boxes looks like the growth of entropy? So why does one, does one necessarily imply the other? I guess as a way of phrasing it. So in a
Well,
world where I have, yeah,
I would say they're not inconsistent, the two. I
right.
mean, I would say I would. Can you go back to the slide you were showing with the complexity graph growing and the artist's impression of what's going on underneath?
Certainly. Yeah. Here we are. Um,
Yeah. So let's look at that. So I would say the real key thing is just to, in the Newtonian representation, to distinguish, well, or the conventional one with scale, is to distinguish absolutely clearly between systems that are in a box and aren't. So the n-body problem, as I said, is not in a box. And so there's a master arrow of time, which is due to the fact that either side of the Janus point clusters form and become self-isolated.
okay.
So now each of those clusters, they all have a birth, and the great bulk of them have a death when they break up. The only ones that don't, generally the only ones that don't are the Kepler pairs. Some live for much longer. I mean, if by some miracle a figure of 8 managed to get formed and sufficiently isolated, that could live forever. So very few live forever, but the great bulk of them will have a birth and a death. And those births and deaths all define an arrow, and all those arrows are aligned with each other perfectly, and moreover with the complexity arrow. And so I would say the complexity arrow is the master arrow, and the ones of the births and deaths of the subsystems are the subsidiary ones, the entrained arrows, if you like. Now, what is very interesting, what is actually happening? So one really characteristic thing in thermodynamics is what is called, which is the virial theorem. And the process, by the way, the virial theorem was introduced by Clausius, Rudolf Clausius. So typically in a thermal equilibrium or close to it, you have virialization, where on average in the Newtonian gravity, what is it? The kinetic energy is half the magnitude of the potential energy. I think that's the way it is. Anyway, it's some fraction of the potential energy. And basically, you don't have exact Poincare recurrence, but the system is just going around more or less, coming back to close to where it was before, and going on like that. So I would say at its most, what I would say the most general characterization of what I would call a thermodynamic system is one that by some means or other, or for some reason or other, is confined. And secondly, it's at least virialized. So what we are seeing in this thing that you're now showing is actually the emergence of thermodynamics. Thermodynamics is not a fundamental theory, it is an emergent theory when systems are confined. So it happens spontaneously in the n-body problem, and it clearly happens spontaneously in the universe. It has created the Earth. We can't escape from the Earth because of we and the Earth's atmosphere can't escape from the Earth at all. So essentially, that's put us in a box, and that's happened by the way that the universe has evolved. So that's the way I think about it. Let me quote here Einstein in his autobiographical notes. He says that the only physical theory of universal application of which he is convinced is thermodynamics, but he adds the caveat within the domain of applicability of its basic concepts. What he doesn't say is what are the basic concepts.
Right. Sure.
So the basic concepts are the damn thing must be in a box of some sort, or it must be self-isolated. And this is what I think has just been completely missed. People just haven't seen that. So I would, you see, the standard view now, I mean, it's put forward by pretty well everyone, Roger Penrose, Carlo Rovelli, and umpteen more, is that thermodynamics applies to the universe, and you can sensibly define an entropy for the universe. Well, I'm very, very skeptical about that. I think there's a whole lot of questions should be answered before you make a statement like that. I mean, for example, Roger says, when he's talking about the entropy of the universe, or at least the entropy within the Hubble radius, he just takes the entropy of all the black holes that are around and just adds. Now, one of the wonderful things about entropy is because it involves the logarithm of the number of microstates, if you have two systems, you can add the entropies and you'll get the entropy of the total. But there's a hugely important proviso, caveat. They must be statistically independent.
Independent, right.
Now, are we so sure that the entropies, that black holes and their structures are independent of each other? Now, just think about
it. I don't think so.
That best matching that we talked about, applied in the particle model, it just says that the angular momentum of the universe must be exactly zero. That means that when those clusters form, which we're looking at now, the angular momenta of all those clusters must add up to exactly zero. And so must their energies. So certainly in those clusters, you can't just blithely assume that they're statistically independent. They're not. But when you have,
so those would be constraints, is what you're saying. That the fact that there's constraints.
When you have constraints that have come about through groups that depend upon arbitrary functions, they become constraints at every space point. So you have, and that's the origin of the Gauss constraint, that in the vacuum macro Maxwell electrodynamics, the divergence of the electric field must vanish everywhere. Yes. So there's correlations all over the place in such a situation, and so I'm very skeptical about saying that you can just add up black hole entropies and say that gives you a good estimate of the entropy of the universe. I would say tell it to the Marines.
No, I agree that this intuition has not been adequately interrogated in most discussions that even I've heard. And now there are people that do emphasize the role the constraints have to play in understanding how best to think about black hole thermodynamics and so forth. So of late, it's been people like Subrat Raju and his collaborators. Ted Jacobson's made some points in this regard, but none of that has yeah, I feel like the sort of confluence has never happened to actually say that, oh, say we have seven black holes in our Hubble radius. Does that mean we can just add their entropies together? I don't think there were, yeah, I don't think anyone's done that calculation in earnest. So yeah, I agree with your intuition that it very well could be that you can't just add them, that perhaps or most likely the constraints do couple them in some sort of subtle way, and that we need to understand that better.
Uh,
So in that in
I
that
think
vein.
I think they could be coupled in an extraordinarily tight way. And there's another issue about black holes, really. Their very definition is teleological, and so far as I know, correct me if I'm wrong, you really need to assume a limit of flat space. That you're talking about a
There
system
are
of space.
Well, there are solutions with positive cosmological constant as well. So you can
Yeah,
have
but
them in both, but you do need to be able to go. Well, you're right that the event horizon is a thing that only makes sense once you know what the infinite future looks like. That there is such a that there is infinite time ahead of us, and then say we lived that long, we'd be able to tell, ah, yes, that was an event horizon. So in that sense they remain teleological, strictly speaking. So it isn't really as much about the flat space as there needing to be an infinite extent of something, either infinite extent of space, like there is in anti-de Sitter spaces, or an infinite extent of time, like in the asymptotically de Sitter spaces. So yeah, that is indeed the case.
Mm.
So and I mean, this is a question that some people grapple with. Like, I guess the people like Abayashtikar and collaborators have grappled with for very long. But I really don't know what the latest or what the verdict is on the alternative notions, such as those dynamical horizons, the all the other notions that they have. I don't quite know if they've sorted this out yet. So yes, that's another, I guess, point of contention that needs to be worked out. But since we're talking about general relativity, could you briefly tell us what replaces the shape complexity when we're talking about the sort of gravitational field in its field theoretic sense?
Well, the there's something in vacuum gravity. There's something called the
Mm,
Yamabe variant. So this was one of the great. I'm told this one of the great achievements of mathematics in the 20th century. The proof. So in 1960, Yamabe claimed he'd proved the following result. Given a Riemannian metric, so one with plus, plus, plus all down the things, in
mm-hmm,
three or more dimensions and a compact manifold.
mm-hmm,
Then he claimed that there always exists a conformal transformation. You change the scale factor at each space point. So a conformal a three geometry has, say, if it's in three dimensions, it's a 3 by 3 symmetric tensor at each space point. Three coordinates tell you implicitly about the coordinate system. Three components, sorry, tell you about the coordinate system. Two tell you about the angles at which curves in the manifold meet, and the third is a local scale factor.
mm-hmm,
Um, and so Yamabe claimed that you could make a conformal transformation, so leaving the angles unchanged, but changing the scale factor, which would convert the Ricci scalar for, this is in the plus 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 case, to the same constant value everywhere
Uh-huh.
for a compact manifold. And then if you multiply that by the, yes, here we're getting here. So it's the infimum with respect to all the different ways you can do it. And if you multiply it then by the appropriate power of the volume of the universe, you get a constant. And that is, it's a function on conformal superspace, and it's an analog of the complexity for the n-body problem. I mean, conceptual. Right. And in my book, The Janus Point, I conjectured that maybe, I didn't know it, but I conjectured that there could be an analogous quantity if you've also got a scalar field in play. And then I said that really, if the ideas that I was proposing in the Janus Point, if they really are true, then if you take all the bosonic fields in nature, would have something that would then be analogous to the complexity in a spatially closed universe. So strangely, only a few months after the Janus Point was published, I was in discussion with Martin Lesurde, who is in, I think he may not be far from you. At that stage, he was in Harvard is it Harvard where Yao is, or is it Boston?
Yes. Yes, that's he's in Harvard, yeah.
Yes. And while we were talking and I talked about this, and lo and behold, he, like you, he can find things which I can't possibly do. He very quickly found a paper by Madame Choquet-Brouard, Jim Eisenberg, and one third person whose name escapes me, which does establish the existence, under certain conditions, on the potential for something like the Yamabe invariant scalar field as well. So that was gratifying that come up. So it remains an open issue about whether that would happen for all the forces of nature. But anyway, that was nice.
I see. Well, no, it's very fascinating. So clearly there's I mean, these, at least for the listeners of this podcast, are points of interest where, you know, someone who's adequately literate or motivated can go try and find such a quantity and you know, added.
Absolutely, yes. That paper by Madame Choquet-Brouard and others was in 2006. I don't know how much longer we're going on. Do we want to get on to these really sky blue ideas about quantum mechanics?
Let's do that since yes, we've come quite far. So yeah, we'll take it away.
Remind me, have I talked about? I haven't yet talked about central configurations, have I? I've just think you have total collisions when all the particles collide together. So a key thing in Lagrange's result, the point is he found that the Newtonian size of the universe, the root mean square length, remains finite at the Janus point. Now, there is a subset of measure zero of Newtonian solutions where it becomes zero. And that is when all the particles collide together at one instant at their common center of mass. That's called a total collision. And that can only happen if when the shape is that of what's called a central configuration. So yes, here's so a central configuration is one in which the force acting on each particle by all the other particles points directly towards the common center of mass, and with a strength which grows with the distance and is such that if the particles are all initially at rest, they will fall homothetically, that means without the shape changing, until they all collide at once at the common center of mass. Now that, I think, effectively that's been known, at least for the three-body problem, since Lagrange's time. What is really much more interesting is that there are also solutions which are non-homothetic. That means that the shape can change, but then just as they all collide together, the shape becomes that of a central configuration. And these central configurations are extraordinarily interesting structures. This is what virtually nobody knows about. I was at a workshop in Germany weeks ago, and I asked if anybody in the audience knew what central configurations were. One solitary person put his hand up, and that was the organizer, Nico Giulini, who did his PhD with Gary Gibbons, who's very interested in these things. And that's how Nico knew about them. So Stephen Smale, the great mathematician, said that central configurations were a great research topic for the 21st century. And I think that's true. So these total collisions, if you time reverse them, they become Newtonian Big Bangs. And a beautiful theory, and it's very, very sophisticated and beautiful theory of these things. Well, they were really realized that they existed at the end of the 19th century, and an incredibly beautiful paper all about them was published in 1918 by the Frenchman Jean Chazzy. That's 11 years before Hubble announced the expansion of the universe. And with it, the idea of a Big Bang. So Newtonian Big Bangs pre-existed the Einsteinian ones. Of course, there's special solutions in general relativity, but I would argue if you take out all of the absolutes that Newton put in, which includes not only absolute space and absolute time, but also an absolute scale, when you take that out, I think it can be well argued that the only solutions that you should have are ones that are total explosions, Newtonian Big Bangs. And they are very interesting. So, and the shape, so the shape has, you really have to forget all about size and just think about shape. So, you know, it's just in the Newtonian representation is ultimately a lie when you say the size is zero, because if it's only the shape, the size is immaterial. I mean, hold up an equilateral triangle at different distances from your eye, and it just looks a different size, but it hasn't changed. Its shape is just the same. So that's there. So let's go. So it's been known for a long time, for at least 20 years, that, well, first of all, those that have the lowest complexity are incredibly uniform. What you see here is one for 5,000 particles and a slice through it on the right. And the density of the particles is very uniform, and then they're perfectly spherical. And it's very beautiful because that's a consequence of Newton's potential theorem, which explains why stars like the sun and planets, if they're not rotating, are perfectly spherical. And Newton was justly very proud of his potential theorem. So this is a far-reaching consequence of that in central configurations. So, that the central configurations with the lowest value of the complexity were very uniform was well known. And the first really indication of that was Lagrange's result for the three-body problem, where it's the equilateral triangle for any value of the masses. And then about 130 years ago, it was shown that it's also the regular tetrahedron. But so Gary Gibbons was one of the people who was very nice numerical paper with Richard Batty and Paul Sutcliffe, who came up with these incredible central configurations, which you're seeing before you in the slide now. And a few people had made, just one or two people had made exhaustive searches for central configurations with just 8 or at most 10 particles. It's very, very time consuming because there's an incredible number of these things. Essentially, the number grows factorially with the number of particles. So for 1,000 particles, you've got 1,000 factorial. That's a rather big number.
Right.
So just hints of an interesting structure were beginning to show in the central configurations with 8 or 10 particles, a bit like a Greek letter lambda, say, for example. So then, and this came about because of my enthusiasm for the N-body problem and talking to Alain Albouy at the observatory in Paris. He thought he would get a student to do actually calculations of trying to mimic a Newtonian Big Bang, which is very difficult because setting the initial conditions is a very delicate task and probably not really possible for a numerical solution. Anyway, so he took on the Spanish student Manuel Izquierdo, and in about May 2021, and because doing dynamical calculation would be so difficult, he got Manuel to sort of get his hand in by finding some central configurations. So by extraordinary luck, Manuel did something which it hadn't occurred to anybody to do before. First of all, he did calculations in 2 dimensions because that makes the calculation much simpler. So he then looked for central configurations, not just only with the lowest possible value of the complexity, but also with somewhat larger values for 1,000 equal mass particles. And if we go on to the next slide, we'll show you what he found. No, sorry, I should say before we do that, let's just go back
Okay.
to say that one of the central the most remarkable one is Saturn's rings in 2 dimensions, where they don't collapse into Saturn because of centrifugal force in 2 dimensions. But let's go on 2 slides, not to that one. That's there, nor that one. Let's go on one more. So this is what Manuel discovered. So this is a central configuration. Those are 2 central configurations. The one on the left is either at the absolute minimum of the complexity or very close to it. And that was no surprise because central configurations like that had been known to exist for over 20 years. What was a big surprise is the one on the right. The complexity in that one is only sort of, they both have complexities which are pure numbers. And it's only about, I think, 0.15 larger value of the complexity. It's only sort of a 2%, 1.5% increase in the complexity to go from that incredibly rich structure. And nothing like that had been seen before. So that was actually a significant, and I think it's going to turn out to be a major discovery in the N-body problem. That is structure in the Newtonian theory. It's nothing to do with, well, it is to do with the dynamics because the dynamics comes from the potential, but it just comes out of the Newton gravitational potential mode scale invariant, and then you look for extrema. So the central configurations are extrema of the shape potential. And so this completely inverts again the story that we know from thermodynamics and statistical mechanics. So in 1877, Boltzmann had his most important and long-lasting insight and contribution to physics, which was that if you have particles in a box, there are vastly more uniform distributions of the particles than non-uniform ones. This is actually ultimately, as Roger Penrose very persuasively and beautifully explains, is the reason why systems will equilibrate. If you start, if they're in an unlikely initial condition, the volume of phase space they occupy will be small, and then if they're moving more or less randomly, they will spread out and fill all the available space.
Right.
So, but now there's an absolutely fascinating application of Boltzmann's situation in a different one. So towards the end of writing the Janus point, I suggested, what about if complexity doesn't just determine the direction of time, but literally is time itself? This is very much in the tradition of trying to solve the problem of time in quantum gravity and get rid of the idea that the wave function of the universe is static. So the idea was to find some internal degree of freedom that one could call time, and its evolution would be like the moving hand of a clock. So I had conjectured that it could be the complexity, so that nobody had proposed that before. So initially I suggested you should look for, you should have a time, the time-dependent Schrödinger equation on shape space. Anyway, let's leave that for a moment and come back to this. Let us ask, so if complexity is time, then time, if time advances, then the complexity must grow. And as complexity is a measure of structure and variety, that means that you must get more varied. And you see that exactly in these two things. You go from the left, which looks like a crystal lattice. By the way, the fact that it's not, the separations are not exactly uniform is just because it's been done in 2 dimensions rather than in 3. In 3, the density would be uniform. So there's one obvious way in which you can increase the complexity, the structure, is just by moving 2 or 3 particles anywhere closer to each other. That will you'll easily increase the complexity, but you will leave the rest of the structure unchanged, and you'll have a boring looking universe. And you will violate the sort of the great ideal of cosmologists, which is to have a universe which satisfies the Copernican principle. It looks the same wherever you are. So then you stop and you think, remember Boltzmann, there are vastly more ways to increase the complexity by shuffling all the particles around in a certain way, but doing it in such a way that you increase the complexity at the same time. Now, by the same Boltzmann argument, that says that you will finish up with a distribution which is uniform, but is structured, and structured in an interesting way. And you see that absolutely exactly on the right. Because if you put a dime down anywhere on that thing there, it will basically, so which has a diameter, say, 1/10 of the complete one, it will basically cover structure, which is the same wherever you put it down, the same nature. It won't be identical, but it'll be of the same kind.
Right.
So you automatically satisfy the Copernican principle. This is meant to be one of the great triumphs of inflation. And it's got there, I have to say, by methods which are increasingly looking a bit shaky now. And this is done in the simplest possible way by just making the Newton potential scale invariant. And so this is, for me, I mean, it's the Boltzmann argument that leads to this appalling end of the universe in heat death of total uniformity. Now we apply a Boltzmann argument, but at the same time say the complexity must increase. and we get a totally different picture.
Wow. Yeah.
So all of this comes from a combination of two things. The universe is not in a box, and we insist on scale invariance.
Hmm.
And in fact, just look at those images, that image on the right. It realizes the atomist's dream. What did the ancient Greek atomists think? They thought there were atoms. Well, they were rather complicated things. They were solid objects. You couldn't cut them in
Right.
half because that's what atom means. They had sort of shapes. They had hooks on so that they could gang up together. And they were falling in the void and swerving at the same time, which would allow something like free will. And they were meant to make the whole of the structure of the universe. I recently started reading Lucretius's De Rerum Naturae on the nature of things. And he has very beautiful, it's a fabulous poem, apparently in Latin. Sadly, I can't read it in Latin. But he talks about, you look at this wonderful landscape with sheep grazing and, and behind it all can be these tiny atoms that are just moving in that way there. And then look at Manuel's central configuration on the right there. That's a pretty good realization of the atomist dream. And this is just done with point particles at the scale and the
Yes.
state potential. So I think we're getting close to the end. I'll just make one more thing. So wait a minute. This is all done without quantum mechanics.
Right. Right.
And as my collaborator Tim Kozlowski pointed out, you're getting effects that look like the ones that in quantum mechanics are attributed to the effect of the Pauli exclusion principle.
Hmm.
It's the Pauli exclusion principle which gives rise to solids and
Yes.
lattice structure. So you've got that on the left. And now if you look on the right, so before Manuel had actually discovered central configurations like the one on the right, I had predicted essentially with the Boltzmann type argument that in such a central configuration, or indeed even for any given value of the complexity, a fixed value of the complexity, all the shortest separations would be the same order of magnitude.
Hmm.
And if you look at that, it's true. And
Right.
what's more, to the eye at least, you see evidence of quantization of those separations. There's a whole lot that are where the particles are close to each other and the separations are much the same. And then you look around and you find ones that are more widely separated. Now, if you go on one or two slides, I think you'll find something which shows. Now, that one, stop there.
The one here
That
or
one
before?
there. So this is one that Manuel calculated for me. This is 100, only 100 equal mass particles. And now I got him to color code, identify. He gave each particle a name. And then for each particle, he found what was its nearest neighbor. And then he colored nearest neighbors according to their separations, just to highlight this effect of what looks like quantization of separations. So you see the red ones are the shortest ones. This is exactly the sort of thing that I'd predicted, because if you put any two particles anywhere too close to each other, you'll just make the complexity too high. And if complexity is tight, that's way out in the future. So then, particularly interesting, you see there's a very beautiful example from the center. You see that thing that's got an egg shape. Down to the left, it's going off still red, but going down to the right, it's going down orange with a wider separation. And those separations seem to have been jumped up by a factor of, say, about 1.2 or something. And then if you go up sort of top left, well, actually sort of in the crutch of that creature, go down a bit. There you'll find three yellow ones. Go up,
Yeah,
three
here.
yellow ones. You see, there the separations are again bumped up by about the same amount, and then go up diagonally, and you'll find four yellow ones. You see that? Now, to the eye, at least, that looks like quantization of length of separation. So, if you wanted to say measure the size of this thing, well, you find the smallest separations, which are the separations between the red particles, and use them and move them around to put next to other ones, or the complete thing. I mean, you could use them to find the measure. In terms of the separation between the red particles, you could find the root mean square length, which is basically what is there, or you could find the typical separations between other ones. Now, I'm hoping fairly soon. Manuel is too busy on his own PhD project, but I'm hoping that somebody else with whom I'm interacting can start doing consistent calculations and see if there really is quantization of length. Suppose it turns out that that there is between, as you go up, so you would make a histogram where you would, and it would be a very narrow one because it's clearly certain. I mean, there's a whole lot of separations which just don't occur.
Right.
So you would say divide up, you would have 100 bins to make a histogram. And my conjecture is that when you fill them with how many separations there are, you would have whatever it is, 10,000 separations or something. You would just put them in the corresponding bins. And I think you would find that there would be just relatively few bins which would be filled and would confirm. Now, if you then were to do this repeatedly for a whole lot of central configurations for the same number of particles, and you find that it's always the same bins that are filled, then this would be quantization of length. And you could say you found a law of nature sitting inside the Newton potential made scale invariant.
Fascinating.
At that conference I was in Germany that I mentioned, with Nico Giulini organized, one of the speakers was talking about these incredible work now with optical clocks, and mentioned the ratio of the frequencies of two optical transitions in one of the favored atoms for optical clocks, and said that that ratio was now the most accurately determined law of nature that was known. It was just a pure number running for about 10 or 11 digits, but it had now been established very reliably. So that's a law of nature. So if we find the same thing happening here, and of course it's still a big if because those calculations have not been done, you could say that's a law of nature, and it's sitting inside pure numbers associated with Newtonian gravity. Nothing whatever to do with the gravitational potential, nothing what only indirectly to do with the laws of, but just inside that but you could say it's just a law of variety. You could divorce this from all talk of gravity and just say, I'm inspired by Leibniz to look for a way to measure variety of the distribution of points in space. The most obvious thing I would choose is the shape complexity. Knowing nothing about gravity, mathematicians in another universe who'd never thought of gravity could come up with it. And lo and behold, you'd find these extraordinary structures, which I have to say are really quite beautiful.
Indeed they are. Yes. So do we want to move on to your most provocative slide here?
Well, all right, yes. Well, this is what it is. So this prompted me to think about how was it that quantum mechanics was discovered? What was going on? Well, the founding fathers, this is very true, because essentially they were interpreting the evidence in photographs taken in laboratories, because particularly photographs in cloud chambers were hugely important in the early interpretation. But as John Bell emphasizes, really all the evidence of that's supposed to be obtained after collapse of the wave function are sort of generalized. They're either literally photographs or they're generalized photographs. And as Bell says, it could even be in the form of printouts on A4 paper, the information, but that's essentially a photograph, or very like a photograph. So what the founding fathers were trying to do was say that evidence in the photographs, what was happening, it had captured an evolving process. It was evolution from an earlier state, which means that really they weren't addressing the infinite regress issue. You'd always have to go early. You could never get back to the original state in this picture. The time dependent Schrödinger equation is, there's no starting point for it. But anyway, this process that is happening in space and time involves the evolution of the positions of particles and the form of the wave function, which is invisible. So that's what they were working on. So this was very standard. But now, looking at the Manuel's central configurations below, suppose instead of the photograph, imagining the photograph taken in the laboratory, you imagine some camera outside the universe that takes a photograph, a snapshot of the entire universe, including just that little bit that's in the laboratory being photographed. So then what would you get? Well, I mean, it may be. So now put a dime down on the central configuration, either on the left or the right. So this is what I call Mach's principle on steroids. Every single separation, what you see on the right, is determined holistically by the requirement that it's an extremum of the shape potential, a variety. And it doesn't even, I don't think it even needs to be an extremum to get the same sort of effect, because it's an extremum, there are a huge number of shapes very, very like that, which are still very close to the extremum, but are just very slightly perturbed away from it. So could it be that there's a completely different explanation for quantum mechanical phenomena? I think it's not impossible.
I see.
And maybe again, and by the way, this as Kozlovsky says, this solves the problem of the collapse of the wave function. If there's no wave function, it doesn't have to collapse.
Sure. Yeah.
So it's I would say it's tempting, and
Indeed, yeah.
It slightly puzzles me that people, particularly like Gary Gibbons, who was very intrigued by central configurations. He was very, very interestingly, if you go back to J.J. Thomson after the discovery of the electron, he was thinking about things very much like central configurations that would explain atomic structure. And in fact, there's a big long paper from him from, I think, 1907. I've got it somewhere on my computer, where he does actually mention Saturn's rings. He doesn't mention central configurations. I imagine there was a German called Jobbik who coined the expression central configuration in 1898. I got that information from Gary Gibbons. But certainly, before quantum mechanics was discovered, they were thinking in terms of shapes, static shapes determined by the joint effect of forces that were a static equilibrium between attractive and repulsive forces. And in a sense, that's what you have in the shape potential, because it's the product of the root mean square length, which gives rise to a hook potential, which could be repulsive, and a gravitational attraction, which is attractive. So
Yes.
this was, I think, shall we say, if Manuel had done his calculations in 1905, I think everybody would be thinking central configurations explain atomic structure, because everywhere you see similar things. You keep on seeing these closed loops. Admittedly, this is here in 2 dimensions, so it'll be different. But there are these filaments in 3 dimensions. I mean, Manuel's found them. You see these closed loops. They're all over the place, and some of them have one particle within them. Some have there. Sometimes there's an equilateral triangle. So at about 11 o'clock, you see there's a sort of a hexagonal closed loop with a bar through the middle and 2 particles above it and 3 below. Yeah, that's it there. If that had been seen in 1905, I'd have think, J.J. Thomson would have gone mad with excitement. Maybe quantum mechanics would never have been discovered.
Indeed. No, it's
Anyway,
very
I guess
fascinating.
it's time to stop on that rather radical
Sure.
note. What do you think, Vasu?
Oh, certainly, certainly. Well, thank you so much, Julian. I've always come away from our discussions with a lot of food for thought, and it is rare to get to talk to someone with a truly novel perspective in our world. It's growing ever more rare. But glad you're around, and well, if our listeners have gotten this far, they should leave a like, share, subscribe, comment, and I'll catch them next week.